Salutations, everyone. Today we'll be talking about L'Hopital's rule, mentioned in chapter 4.7. L'Hopital's rule is one of my favorite methods since it embodies the spirit of the mathematician. Through pure brute force and getting from point A to point B, L'Hopital's method is a method essential to the basics of calculus, especially when it comes to finding limits of indifferentiable equations. Let's get right into it. L'Hopital's rule was a rule made in the late to mid 1700s. Who was L'Hopital? L'Hopital was a French nobleman from the mid to late 1700s. He was educated in the top universities of Europe. He was also, at his time, a well known mathematician. He had studied in many places, such as the University of Paris and the University of Austria, but also a master's from the University of Stuttgart. L'Hopital was a rich nobleman who also had a key taste in math and getting his name into the math textbooks. Fun fact though, L'Hopital actually did not invent the L'Hopital method, and he only paid for his name to be put on the method. L'Hopital himself had nothing to do with the invention of L'Hopital's rule, other than financial incentive given to the university of which the L'Hopital method was found to put his name on it. L'Hopital was in fact found by a less well off, less fortunate, commoner mathematician. But due to L'Hopital's deep pockets and capitalist greed, he was able to get his name on the L'Hopital rule, therefore making L'Hopital's rule. Let's start off with the basics of L'Hopital. Now let's look at this formula right here. Limit x to the 0, e to the x minus 1 over x. Now, if we go ahead and try to solve this right now, this question is asking us to find a limit as x is going to 0. And right now we have two x's, an x on the top and an x on the bottom. We also have e and 1, and it is being subtracted. So now let's start off and trying to solve this. Let's go ahead and start with the proper procedures for getting the limit. For the limit, you are supposed to get as close to the key variable inside the limit bar. The limit bar is in the bottom to the arrow. Now let's start with that. With the limit, as you can see, it gets plugged into the top section. Going back to the original, see how I can do that. We see a limit right now at x to the 0. If we plug in x for 0, we can see that e to the x becomes e to the 0 minus 1 over x. E to the x becomes e to the 0. And as we know from our rules of algebra, anything to the power of 0 becomes 1. Therefore, that would mean e to the x minus 1 becomes 1 minus 1. As we see, due to that second one, which the arrow is pointing at, 1 minus 1 becomes 0. And that is it solved for the top of trying to find our limits. Now let's go and try to solve the bottom. Let's go and plug in 0 again. X to the 0, 1 minus 1 over x. X is 0, so 1 to the 1 over 0. Now let's see that. 0 up top, because those two cancel out. Now we plug it in for the bottom. 0 up bottom. Now we have 0 over 0. But the answer doesn't seem right, because we don't usually plug in 0 for the bottom or the top either. Or anything over 0 is 0. Anything divided by 0 is invalid. So this equation, as we can see, from plugging in 0 to the top and the bottom, is 0, 0, 0, and is indifferentiable. What is the limit then? Because 0 over 0 isn't exactly a limit. We can't find the limit. Or can we? We can find the limit. If you look at this original equation right here, this is the basic form. As x goes to a, f to the x and g to the x are subjected to that. But for not all cases, you can solve that. As we saw earlier, as 0 over 0 made our equation indifferentiable. Having 0 over 0 is not a valid answer. Now, let's see what we have in our pockets to solve this. Unlike L'Hopital, we don't have pockets full of cash, but we do have in our pockets L'Hopital's rule. Now, what is indeterminate? Indeterminate, I've mentioned a few times, and if you want to pause the video, that's a better description for you. But indeterminate is when we get to a point in a function where it is not a correct answer. And we cannot take that answer because it doesn't apply to the rules of math. Anytime a function is indeterminate and we're trying to find our limit, L'Hopital's method is to be used. So, as we see, that is the standard way we did our equation before. F of x over g of x. And what did that get us? An indeterminate answer. So, what can we do now? Of course, no deep pockets, but we have L'Hopital in our pockets. So let's see how we can apply that. So we already tried the original method of limit of x to a, and that didn't work out for us. Now let's see what we can do. As we can see, we tried that method and it was indeterminate. Now let's see what L'Hopital's can do for us. As we see here, these two functions look very identical, but the key difference is the function on the right is L'Hopital's, and the function on the left is not L'Hopital's. The function on the left is the previous function we used, and that function got us an incorrect indeterminate answer. The function on the right, as you can see, is f derivative of x over g derivative of x. Both the denominator and the numerator have the denominators and the derivatives taken from them at the same time. That means no simplification before taking derivatives. Now, you might wonder, how would that change the final answer? Well, let's see. As we see, going back, circling all back around to our original equation, which we were not able to solve the first time around, now we're going to try to use L'Hopital's method, which is on the top right. On the top left, as you can see, was our original method. Now let's go and apply that to L'Hopital's method. Let's go ahead and start doing this all over again, but instead of using the top left function, we're going to use the top right function. Now let's go ahead and start with the limit. We have it going to 0, which is a. But instead of plugging that in, let's go ahead and apply L'Hopital's, which means getting the derivative first. Now let's start with getting the derivative of the top. E to the x, as we know from our calculus, is just e to the x. So that stays the same. Now we have to subtract it by 1. And as you can see, 1 over here, the derivative of 1 is 0, or dne, non-existent. So now for the top, we have e to the x minus 1. And that disappears, which becomes e to the x plus 0. So now we can now move on to the bottom part. So let's go and combine that. We have it combined now. Now to the bottom. Now let's take the derivative of the bottom. The derivative of x each time is also turned into 1. derivative of x equals 1, as you see using the method on the top right of L'Hopital's. So now we got the derivatives of the top and bottom separately. Separately. Keyword separately. Because you see last time we added them all together and then got the derivative. Main things to change the orders. Because the top two look very similar, but very different answers. So now the bottom becomes a 1. E to the x over 1. Now, applying L'Hopital's to that, we have e to the x and we have 1. So first step is already now complete. Now, e to the x over 1, using our fractions and our knowledge of algebra, that equals e to the x. E to the x is something that we can work with now. Now, key thing here, if we try to apply the limit again and we get an answer that leads us down to the path of L'Hopital's again, we need to use L'Hopital's multiple times. There's multiple questions out there where you need to use L'Hopital's more than 2 or 3 times, or even more. But L'Hopital's is not a one-time solution, depending on the problem. Some problems you'll be all right with applying L'Hopital one time. But as we can see here, we need to check if we need to reapply L'Hopital's. So let's try getting this limit again. E to the x is going to 0, the limit of 0, e to the x. Now let's try to work with this instead of our previous equation. We have x and we have 0, like our previous equation. Everything looks the same so far, so let's go and plug it in for x. X on the top, when we're plugging in 0, is e to the 0. The limit of x to 0, as we can see, is like before. But let's see what answer gets us. As we can see, e to the 0 is 1. But now, since we apply L'Hopital's, there's no other factors in here that can make this problem indeterminate. So let's see where we go from here. So now we get rid of this e to the 0. We turn it to 1. So this finally now means that the limit of 0, when x is headed to 0, of e to the x minus 1 over x equals 1. As you can see back here, these two are both the same function, but one has been applied L'Hopital's and one is regular. This one is unsolvable. This one with L'Hopital's is solvable. So now, as we can see, e to the x minus 1 over x, the limit of x heading to 0 is 1, using the method on the top right. The method on the top right is L'Hopital's. The method on the top left was the regular method that got us the incorrect answer. So now we can see top left we used got us 0 over 0. 0 over 0 was the indicator to use L'Hopital's. There's multiple indicators, such as 0 over 0, infinity over infinity, infinity over 0. These two are the most common ones you'll see for applying L'Hopital's. L'Hopital's, these are the key signs. There's 0 over 0, infinity over 0, because both these answers are indeterminate. And if you see these and you keep getting these answers, you will keep needing to apply L'Hopital's to undo these problems and get the proper answers. But there's also multiple other things that can happen to lead to L'Hopital's. Let's take a look at that. As you can see, 0 over 0, infinity over 0, is the most common factor of that. But as we can see, there's multiple other things that you can do. You can do 0 times infinity, infinity minus infinity, 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. As we can see, these will all use various forms that relate closely to L'Hopital's method to get the final answer. Now, as you can see, L'Hopital's is a very straightforward and brute force method used to find an indeterminate or uncooperative limit function. Therefore, in conclusion, L'Hopital's method was a method invented by a common nobleman mathematician that was later stolen by L'Hopital due to his deep pockets and therefore is used on limitation functions that are indeterminate to therefore get the proper notation and proper function where you can take the limit of zero or not only zero, any number given to you, to finally get to a form where L'Hopital's is no longer required and you can take the proper limitation of the function. Therefore, in conclusion, L'Hopital's is a key method used for both limitation notation and calculus. Thank you. Have a nice day.